testable theory of species. Under what conditions would you say two varieties belong to the same species? Under what conditions would you say they belong to different species? These can be answered in two different statements. So if you say, if you observe such and such, I will say that A and B belong to the same species. But if you observe something else, such and such, I'll say they belong to different species. Right? So I'm separating the sufficient and necessary conditions. Unless you state those conditions, none of this is testable. They are like Freudian psychoanalysis. Any evidence is still compatible with it. So what is it? Under what conditions would you say two things belong to the same species or two different species?
Some defined percentage of similarity in DNA or something.
Why should that be the case? For example, could you say, is it like height? At some point you say above 5 feet and below 5 feet. That's arbitrary completely. The question to ask is, let me step back and say what we are trying to do is to investigate how to construct theories, right? And we began by asking the question, how do you come up with arguments for evolutionary theory? And then we discovered that you need, in order for evolution to work, evolutionary theory to work, you need a theory of species. And a theory the first question to ask is, what does the concept of species explain? So let me give you an example of what that question means. Okay, let me take a simple case. You are told that magnets have a south pole and the north pole. Whether it is south or north doesn't matter. This is, let's call it negative and positive poles. Magnets have two poles. Right? You cannot observe poles, right? These are theoretical constructs. And then you are told that similar poles repel and opposite poles attract. This is part of high school textbook. But to that you have to assume that two minuses are similar, two pluses are similar, and the minus and the plus are opposite. Why do we need that? What does it explain?
Explain why sometimes magnets will repel and why other times will attract,
So,
depending on the orientation.
Yeah, so describe to me. This is your theory. What are your observations? What do you want to explain? Let's write that down. This is an important discipline to be able to state the observation generalizations without referring to this. So what would you say are your observation generalizations? Behavior of magnets.
You have suppose two bar magnets.
Uh-huh.
Then
So there is a bar magnet and there is another bar magnet. Okay.
you bring two sides together and they repel each other. But you turn or change the orientation, you
Uh-huh.
bring them together, they attract.
Okay. So I'm going to mark these as blue
Yeah, blue and red.
and red. And this I'm going to mark as red, whatever, some color. Actually, to make it simpler, I'm going to mark this as green and pink. Because otherwise, I'm cheating.
Similarity.
So now state the generalization. If you bring red and green together, they attract. but if you bring green and blue, they repel. And if you bring red and pink, they repel. So there are systematic relations. So the observation would be blue plus green repel, blue plus pink attract, red plus green. Given this much, if your theory is correct, it should predict if you bring, given that blue and green repel, red and green should attract, right? And if you have red plus pink, they should repel. And the claim here is, an observational generalization is, take any two magnets, put four colors like that, and this is the configuration that you're going to see. This is your observation. That will give you, so you can say, if I assume that one of them is plus, the other is minus necessarily, then everything follows. Yes? Right. Now, that doesn't tell you anything about South Pole and North Pole. So what are the facts about South Pole and North Pole?
We can replace the colors, we can interchange the colors, and we see that irrespective of what those colors are,
Yeah.
one part of the magnet behaves the same way.
Right. So I mark them as minus and plus arbitrarily. Right? The only thing that the theory is saying is that in every magnet, there is a plus and there is a minus. How do you determine which is plus and which is minus? And the theorist would say, I don't care. You can mark any of them as plus and minus.
I mean, even now, if all the magnets you interchange the polarity, I mean, all the magnets in the world, if you interchange the polarity right now, it won't make much.
Not all the magnets. So you bring me a magnet, I will arbitrarily say this is plus, that is minus. You bring me another magnet, I will say this is plus, that is minus. Can I do that? No. Why not? So notice I have explained that thing. But you're saying that it is not simply an arbitrary opposition. There is something about minus that should be the same in all magnets.
All magnets, yes.
Yeah, you cannot assign plus and minus arbitrarily.
Suppose you have two magnets and you bring both of them close to each other.
Yeah.
You can, and if they repel, you can name the adjacent, the sides which are close to each other as minus.
As one is minus, the other is plus.
The other
But
also
bring
is
another
minus.
thing so I can do this arbitrarily.
No, I am trying to say
Make
this.
a
Yeah.
magnet rotate freely in Earth's magnet. Okay, do not assume Earth has a magnetic field, but just take a magnet, leave it freely. If it points in a particular direction, that
Okay.
pole is north, the other pole is south.
So the second observation is orientation of E. So take any magnet, hang it on a string, then you find that one edge always points to the north, the other one always points to the south. And so I'm going to the one pointing to the south I will call North Pole, and the other one I will call south. So that means it is not arbitrary. That means there is a connection between these pluses and minuses and the way a free magnet orients itself. Right? Now there is an interesting prediction. Given two magnets, if you have two magnets, this is pointing towards the south, this part is also pointing towards the south, then you make the prediction that if you bring these two, they will repel. So it is not arbitrary. There is a correlation between the orientation of a magnet and the repulsion attraction behavior. That is how you build the theories. That's why it is important to separate data from the theory. That's what I mean by explanation. You invent these entities in order to explain what you observe. Okay? In people call it explanandum and explanans. The terminology doesn't really matter. What it means is what you need to explain and the propositions that give you the explanations. And to go back to what we have been doing, this is like the definitions and axioms of a mathematical theory, and this is like the theorems that you derive from here. And these are the predictions. Theorems in mathematics correspond to predictions in science. And when the predictions match your observation, you say the theory explains the observations. So without clear articulation of the observations that you want to explain, there is no theory.
Yes.
Yeah.
Similar poles repel and opposite poles attract. What is it? Is it a theorem or?
No, that's like this. You are inventing stuff. This is not what you observe.
No, what is it? What do you call it?
The theory.
No. Are they axioms or what are they?
Like axioms and definitions, corresponding to axioms and definitions, except this. The difference between science and math is the following. In math, nobody is going to ask you what is the justification for your definitions and axioms. All that you're saying is if you take these axioms and definitions, such and such conclusions will follow. In science, that is not sufficient. You have to show that the axioms and definitions that you set up will correctly predict your observations. That condition is absent in math. Math is not committed to explaining anything in real life. Science is.
So this gives
Yeah.
a pretty math, there is no observation part then.
Yeah.
So this way of theory construction doesn't work in math.
No, it does work. I mean, there is a common part in math and science. Both scientists and mathematicians, the theory constructors, set up these imaginary worlds and derive the consequences. And mathematicians, once the theorems are derived, their job is done. In science, the theorems are derived, theorems are called predictions, and you have to show that these predictions match observational generalizations. So it is not enough to predict, you have to show that the predictions are true. In math, how do you show that the theorems are true? By simply deducing them from here. These two parts are separated in science. You deduce them to give the prediction and show that the predictions are true by comparing them with the observations.